Cabin pressure, go. Fuel systems, go. Oxygen, go. All systems, go. Alan Shepard, May 5th, 1961. Okay, Houston, we had a problem here. Jack Swigert, Apollo 13, April 13, 1970. Hi, I'm Frank Spidell, retired emergency physician and recovering hospital administrator, and welcome to The Doctor Is In. The program's intent is not to practice medicine and provide medical advice. With the help of our guests, we hope to provoke respectfully informed discussions of healthcare to benefit our community. Now, we are awash in systems. They abound. They are everywhere. We use them, and they use us. And we are a system. The definition of a system can be quite simple, even elemental. A group of interacting elements that produce something. Yet the description of systems evolve, expand, and mutate without end. And informative experiences is in a search of Amazon for books on systems. The spectrum is massive, and that's just the authors. It ranges from the director of the Johns Hopkins Applied Physics Laboratory to a phantom who just likes to write. There are some systems that are trivial, some that are vital to our well-being. The brakes on our cars to the lunar landing module are vital systems. What qualities should those vital systems have? To help us understand the role of systems in our lives and needed qualities for vital ones, I am honored to have as our guest today Mr. John Bondi, former Senior Engineering Manager for the Boeing Company. Mr. Bondi graduated with a degree in mechanical engineering from the Cooper Union in New York City. He started his career as an engine performance analytical engineer at Pratt and Whitney, and then went to the Boeing Company in Ridley Park in 1985. He spent 35 years working on the design and development of helicopters and tiltrotors. He worked a number of development programs throughout his career, ultimately rising to senior management roles in engineering and program management on the V-22 Tiltrotor program, where he led the development of the mechanical flight control systems. Mr. Bondi retired from Boeing and does consulting, and he leads the aircraft restoration team at the American Helicopter Museum. Mr. Bondi, welcome to The Doctor's In. What did I get wrong?
Good morning, Frank. Thanks for having me. It's an honor to be on your show. What did you get wrong? Nothing. You nailed it. As you point out, systems are all around us, and they encompass numerous things. They can encompass, I'm here to talk about aviation, aircraft, and things of that nature. But of course, systems apply to, political systems, biological systems. They're all around us, and they're both at multiple levels too. You can have a system that encompasses multiple subsystems. So, what drives a system is what are the requirements of the system? What is the needs of that system?
I was noticing on one of your notes that are one of your visual supplements here. The systems are also, we think of them as mechanical, but they're also social and personal interactions too.
Yes.
I was very much aware in the emergency department, you have to have a system to get things done. Mm-hmm. Otherwise the chaos is amplified. Humans make mistakes. Yeah. Some of us see systems as a way to mitigate error. What's been your experience in this?
Systems are designed to do a certain function, and if you can define a requirement for that system accurately, that function will be performed with its intended purpose. If the system has errors in its requirements, its design, or its test, the system can fail. But we learn from those failures and try to make the system better. So, as you point out, systems do evolve. In some of the programs I've worked on, we've had initial requirements, but then the program evolves as the requirements change, but also as we discover issues with the design, the system will mature and be improved. Yeah.
I have to apologize to our viewers as I do a side monologue for a second. One time I was involved in one of my hospitals putting an IT system in to support decision-making process. And they did it without input of the people who were going to use the system. And nobody used the system. The thing was clunky. It didn't help, but you had to work for the system. as opposed to the IT system working for you. And I thought that the design for that system occurred without the people who were using it, who were going to use it, who had to use it, having any input. Lessons learned.
Yeah, sometimes the system can channel you or funnel you into an inefficient operation.
Yes.
Where it's not, it's not the ideal system because you're using a system that really wasn't designed for what you're doing. The requirements were old or antiquated or just erroneous.
Yes, exactly. Getting the people who are going to use it seems to be a big help. Some have spoken of systems as being fail-safe or fail-prone. What's been your experience with those two terms?
Well, fail-safe is a term that describes it. If a system fails, does it fail into a safe mode? A good example, an early example in terms of a mechanical system would be the elevator. Elijah Otis developed a brake on an elevator that if the cable broke, the brake would automatically engage. Just by the nature of the way it was constructed, the brake was connected to the cable. If the cable broke, the brake would engage. It was basically fail-safe. So that was revolutionary in terms of the ability of elevators to be incorporated. People knew that elevators were needed to make buildings bigger. But no one had a fail-safe design. That design allowed, big cities to develop, tall buildings and skyscrapers. So that's kind of an early example of fail-safe. When we talk about, say, aircraft programs like, say, the V-22 or some of the other aircraft that are out there, commercial aircraft, redundant systems. You have backup systems, hydraulics, for example. Hydraulics control the flaps and the control surfaces on aircraft. If you lose a hydraulic system, you'll have a backup system that will engage. So in some cases, you cannot have a system you cannot have a backup system. For example, in a rotor system on a helicopter or a gear in a gear train in a helicopter, those are single point failures. So those are what we call critical parts in our business. And those we deal with in a different way. If you can't have a backup system, you put extra integrity and extra focus on those parts. You have increased inspections. Metallurgically, for example, on a gear in a helicopter transmission, you'll have something called triple melt steel.
What's triple melt steel?
So what you'll do is when you're melting the steel and forming the ingots to cut the gears, what you'll do is you'll melt the steel. You'll let the impurities settle, and they'll settle, and some will rise to the top. And you'll let that steel cool, and then you'll cut the top off, and you'll cut the bottom off. That's typical. But in terms of helicopter gears, you'll do that 3 times. You'll take that pure ingot, you'll do it again and again and again, triple melt, to avoid any inclusions, any cracks, any impurities in the metal, so that you won't have a failure in operation in that single point failure, that critical part where you cannot have a specific backup system. You'll put extra inspection. You might also put life limits on that part, so that it's only in the fields X many times or X many cycles. You'll inspect it periodically, you'll add extra design margin to that part. So instead of say a margin of 1.2, it might have a margin of 1.7, 2. Much higher. So that's how you deal with, let's say, single point failures. But with systems like hydraulics, where you would have a backup systems, usually 3. Usually there's 3 systems, backup 3 systems on a aircraft hydraulic system, 2 backups and 1 primary.
All this is dependent on people that do the inspections, doing what they're supposed to do, following a protocol.
That's right, and that's another system. A protocol is a system too. So is that part of the system? The systems are embedded in systems and overlap. When you're talking about a complex system, say like a V-22, there's inspections. There's did you get the requirements right? Yeah.
In the Navy, we used to have a spot check program. I was a medical officer. I had like 44 spaces on the carrier that I was responsible for the material condition thereof. I know nothing about ships and stuff like that, and I relied on other people to help me out to get the job done. And one of the things I was fascinated with was to do it the right way. You just didn't inspect your work or your maintenance of it. You brought somebody else in who wasn't part of your department to look at it with a fresh set of eyes. And oh yes, once in a while you'd bring in, we called that the spot checker, we would bring in somebody else to spot check the spot checker. Mm-hmm. You can never look at critical systems too often, can you?
No. And that's a good point. Checking is important. In the engineering process, a drawing, for example, is done by an engineer. Then there'll be a checker that will check that drawing. And then maybe it's checked again. So there's multiple, we try to have multiple checkpoints in order to try to eliminate the human error factor.
I remember sadly, I think it was Alaska 93 that had a failure of the jacking screw system. Mm-hmm. And I think that was the Alaska Air had outsourced from Alaska Air proper the maintenance checking of the different parts of the plane. Mm-hmm. And apparently the first person that saw the jacking screw said it was worn and had to be replaced. Mm-hmm. And his supervisor came along and, now, it's still got life in it. We can run it a while yet longer. It was only a few flights after that they completely lost the jacking screw, mm-hmm. which was a catastrophe. We are as good as the checks we do. That's and the people we work with. Mm-hmm. I've seen systems described as being stable and unstable and neutral. What is that concept?
Well, I have a graphic. If we can show that, showing what
I think I'm familiar with the graphic. It shows the input.
Yes.
And the input's a constant level of input of something.
Basically, stability is how does a system react to a disturbance, an input, any kind of anomaly, or just normal operation. Is it, not necessarily an anomaly, but just normal operation, a normal input. So an unstable system could oscillate and tilt destruction. A stable system an example of a stable system would be, say, your car suspension with, where you have a spring and a strut and they're in good condition. You hit a bump, the car hits the bump, and it absorbs the bump, and there is a movement within the cabin of your car, but it settles out immediately because there's a spring and there's a damper, and it damps it out instantaneously. A example of, say, a neutral system would be if your strut was worn and you hit a bump and you just kind of continue to oscillate as you drove down the street. Not necessarily catastrophic, but it still kind of wobble. And you've seen cars like that on the road, right, where they hit a bump and they continue to wobble down the road. And then an unstable system where it just something will take an input, but then the oscillation will feed on itself. There'll be positive feedback that will cause the continual absorption of energy into the system until it self-destructs. A good example of that would be the Tacoma Narrows Bridge failure. We have a video of that. That's always an interesting historical event that really informed the civil engineering community over the years and how to deal with inputs into structures. Vibratory inputs into structures.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only at 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
Let me see if I got this right. The stable and unstable systems and a neutral system. If I had a marble on the tabletop here and I put a force to it and I displaced it, that would be an example of a stable system in the sense that after friction, the marble would stop rolling.
Yes.
Would not accelerate. It would not. It would not be damped to no movement. If I were to have that same marble placed in a bowl and I displaced it up the wall of the bowl and released it, then it would come back down to the center of the bowl again, maybe oscillate a little bit, but that would be a stable system.
Be stable. A little bit of oscillation, but stable.
A little oscillation, stable. Yeah. And if I inverted the bowl and balanced the marble on top of the bowl and then displaced it, it would accelerate and go down.
Yeah, it's an unstable state, and it would.
And I guess critical damping is going to be a big consideration when we're looking at system stability. And you've got that great diagram where we displace something and then it trails back after time and gets to the neutral position again. And the Tacona Bridge is, I think, a wonderful demonstration of you can put energy into a system, and if the energy is put in at the same rate as the frequency of the system, like if we had a swing, and the swing is going back and forth, I can increase the amplitude by putting more energy into it, but it has to be at the same frequency as the swing is moving back and forth. Otherwise, I'll damp it.
Kind of like positive feedback. For example, pilot-induced oscillation, where a pilot will react to a disturbance, but he'll be slow. So by the time he reacts, that disturbance may be acting in the same direction that he's trying to counteract. So he will induce an oscillation just by his reaction. Instead of the system might naturally damp out, the pilot, because of his reaction time, because as a human reacting to a system which is somewhat faster in terms of its maybe frequency than the pilot, they can actually amplify that oscillation. And you can see that in pilot-induced oscillation videos of aircraft.
I had to ask, this is beyond the topic. Do you feel comfortable flying?
Yes, I do.
Okay.
Absolutely.
Great. I'm glad to hear that because I am more stressed by flying than I ever was before. When you're on final and you're getting all these big corrections in the last bit there, I start to have anxiety. But so far, I'm still here to talk about it.
And that's the good thing about systems, aviation systems and air traffic control systems, that incidents that have occurred over the years, that they've all been built back, they've all been addressed and built into the system to continually make it more robust throughout as it evolves. So I think we have a very mature and safe aviation system.
You were wired deep into the Osprey program. I can't imagine with all that unbalanced angular momentum there, trying to balance it and get some stability to it. What was the biggest challenge in that program?
The biggest challenge, there were numerous challenges. If you look at the configuration of the V-22, it takes off like a helicopter and then converts into an airplane. That alone makes it complex, And why do we do that? The requirement for that aircraft was to go long distance and to go fast, but also to take off and land vertically. So that's quite a unique set of requirements that you're trying to bundle both a helicopter and an airplane into that single platform, and that was driven by, if you go back to the 1980s. The Iran hostage rescue mission Operation Desert Claw, which failed, and due to the fact that it was very complex, the aircraft could not go the full distance from offshore into the Iranian embassy. They had to stop, they had to refuel, adding complexity to that system as a mission. The Marine Corps decided that they needed something that could address those shortfalls, and the V-22 came out of that. What was the hardest part of that system? I think there's a lot of issues that were different in that which one was the toughest. Vertical engine operation was engines usually operate horizontally. The oil system alone was complicated. The number of gearboxes were complex.
Wow. I hadn't thought of that.
Yeah, and but if you also look at, as the aircraft matured, different operators took that aircraft. So the Special Operations Air Force started operating that aircraft, and they operated that aircraft in a much more a desert environment. Instead of landing on airfields or embassy roofs or what have you, they would land in desert environments. Sand and dust became a big issue because of the what we call the high downwash of the V-22. Mm-hmm. So we had to deal with filtration for the engines. We had to deal with numerous issues relating to sand and dust. So there are a number of issues with the V-22, all which we worked through and resolved. And the aircraft again has evolved. Different customers have come along: the Japanese, the Navy, and as you pointed out, systems do evolve and requirements change, and the system can be adjusted to a certain extent.
The prop/rotor for the V-22. Mm-hmm. Does that combine traditional prop configuration? Can you use the same configuration for a prop as you do for a rotor? It's
a hybrid. So a helicopter rotor is quite much larger than an airplane prop, and the pressure ratio across a helicopter rotor is quite small compared to that of a prop. So that's because just based on when you're flying an airplane, you want a high pressure ratio for efficiency. But for a helicopter, you want a large diameter and a low pressure ratio. You don't want to lift up too much dust and gravel from the ground, but you also have to lift up a large aircraft. So you want what we call a large rotor. Combining those two, if you look at a V-22 rotor, it has aspects of both. So it's a compromise. The aircraft is a compromise from that perspective. So it does a unique mission. It is a compromise. It can fly quite fast. It can go quite a distance, but it does have compromises with respect to its operation as a helicopter and its operation as an airplane.
Did you ever feel when you were looking at a mission or a customer's needs that you were trying to design a perfectly smooth elephant of negligible mass that could fly at 0.99 the speed of light?
That's a good analogy.
Marines, for some reason, always seem to want a perfectly square circle. Along with the Osprey, they also had an AV-8B Harrier program. And I always felt bad for those people flying those machines. They had a higher alpha rate. They had a higher mishap rate. Mm-hmm. And I often looked at them, and when I was watching them hover, I thought, boy, if that is an unstable system waiting to decide to have going to zero, I don't know what was. I respected those people tremendously for their skills.
It's like balancing on a pin, so to speak. It's very the Harrier with its
yes,
and the F-35 version that replaced the Harrier also is a impressive system with respect to vertical takeoff and forward flight that is tough to design.
I would think it's tough to find people who are not going to be doing pilot inputs that are going to make a unstable.
Well, with digital controls, you can address some of the pilot frequencies and the pilot inputs.
Great.
So that you can minimize that. you know, we can deal with that in terms of software and filters and the flight control system that deal with that. And just flying a tilt rotor and the conversion and from airplane mode to helicopter, you need digital controls to enable that functionality because it is so complex. You know, without all the augmentation of a digital flight control system, the V-22 would be very hard to fly.
So tell me about digital controls. When did they start becoming used effectively? When is this something from the 50s? Or
no,
something?
it's more from probably the 70s. You know, the concept of tilt rotor was existed. You know, and prototypes were built in the 60s, actually in the 50s. If you look at some of the history, 50s tilt wings, tilt rotors, they existed in the 1950s. They did very limited number of conversions from helicopter mode. They would fly them in helicopter mode, and then they did limited number of conversions into airplane mode. But they were always touch and go with respect to the capability of it enabling to do that, to go from one mode to the other. Digital controls that were developed during the Apollo program and later, and as digital technology developed. Digital flight controls in the 1980s really enabled V-22 and F-35 and some of the modern aircraft to exist from a flight controls perspective.
As we started out, we taught that humans, by nature, we make mistakes. And there's a system that is kind of dampening our mistakes, our tendency to overcorrect or to be slow in our correction.
Exactly.
Speaking about interfacing with humans, what's CRM? I see that term all the time.
Cockpit resource management. That really is a term that is focusing on the interaction between a pilot and a co-pilot to manage all the data and all the controls that come into a cockpit in an efficient way. If you look back at history of aircraft accidents, for example, United Airlines 173, where there was a pilot, a co-pilot, and a flight engineer, and they had an issue with the landing gear light when they put their landing gear down. And if you look at what happened on that flight, they put the landing gear down. There was actually a broken actuator, so the landing gear dropped very violently. It actually locked, but it broke the lock indication sensor. So they did not know in the cockpit that the gear was down and locked. They put the gear down using the handle, but they did not know. They did not get a positive indication. They spent the next, and they were on of course, since they put the gear down, they were on their way to a landing. They spent the next almost hour trying to figure out what was wrong with the gear, trying to figure out if there was something wrong with the light. They were circling. The flight engineer and the co-pilot noted a number of times that the aircraft was low on fuel. The pilot was still obsessed with the fact that the landing gear was maybe not down, maybe not down, until they realized that it probably was down. They started an approach, and then they got an indication that their engines were flaming out, and they crashed. And the investigation determined that there was insufficient communication between the pilots and the co-pilots and the flight engineer. Well, the flight engineer and the co-pilot knew what was happening. They were not forceful enough with the captain, and the captain kind of dismissed their concerns. So CRM was developed actually as part of a recommendation out of that report. And CRM was to say, the pilot is not a dictator. The pilot is a manager of a team. He needs to delegate to the team. He needs to assign roles to each member of the team, and he needs to listen to the other members of the team. So that really was the impetus. UA Flight 173 was the impetus for CRM. And courses were developed, and it became a requirement for pilots to take those courses and to understand. And in addition to that, the cockpit itself has evolved. not just the CRM, but the cockpit indications like lights and warnings. And no longer would you just have a light that says fuel is low. You'd have annunciations, you'd have buzzers, you'd have cross-checking, between sensors. So there would be a lot more indication within the cockpit that something like that is happening. But with respect to the incident on that aircraft and the pilot, CRM was developed really focusing on the interaction between the pilot and the co-pilot.
Good to remember, good to carry forward, and it exists not just in aviation, it exists in healthcare too. Mm-hmm. Unfortunately, there was a case, we have built up layers, redundancy. Mm-hmm. How many times when you go into the hospital do they ask you your name and your birth date?
Mm-hmm. Many times.
We still get it wrong. Mm-hmm. I have first-hand knowledge of a case where a pneumonectomy, removal of a lung, was done on the wrong lung. Mm-hmm. And we have so many things that were done and followed to make sure that we don't have wrong site surgery. Mm-hmm. The anesthesiologist, the scrub nurse, the charge nurse for the OR that day all said it's a right pneumonectomy. And the surgeon had a screaming fit. He was a terror. Mm-hmm. And he buffaloed them, and he had the patient flipped, and he took out the wrong lung because he knew what he was doing. It's very hard. Sometimes if you have people that speak up and say, no, it's a right pneumonectomy, sometimes people can be, but you have to have a special kind of person that will look to the surgeon who's already been throwing instruments now and say, no, this is, you're wrong. And I guess we have to have a way, and one of the things I learned from that is when things go bad like that, there has to be some kind of a buzzer that's available for people to slam to get other people mm-hmm. to come in and interact and get the team back down to the level of reflection and not anger.
Yeah, it's a matter of training and to break that mold of the dictator mentality. I think you had asked me beforehand whether CRM works. A few years later, after CRM had been implemented, there was United Airlines Flight 272, I believe, which is another notable incident where the DC-10 aircraft was flying, and a failure of a engine disc in the back of the aircraft, in the center body of the aircraft, destroyed the hydraulic system, all three hydraulic systems. So right there was when you go back and talk about, backup systems, it turns out there were three systems in the aircraft, but they were all co-located. System separation was not always a big focus in civilian aircraft. It is in military aircraft, obviously, because of live fire and things like that.
A-10s.
Right, exactly. So with respect to that incident, the pilot at that point had no controls. This pilot, I think his name was
Did they land by just changing the power on the engines?
Yes, and the way he did it was he didn't actually do that himself. He assigned roles to each person in the cockpit. He looked for feedback. There was a pilot, an experienced pilot, who had looked at a similar accident on an Air Japan flight in the back in doing a flight, and he was a passenger, and he informed the stewardess that he could help. And the stewardess told the captain, and the captain invited him right into the cockpit and said, "Glad to have you." And he created a working environment there where that pilot was able to, as you point out, was able to operate the engines using differential thrust to enable to steer that aircraft to a runway in Sioux City, Iowa, I think it was.
Is this the one where the ATC, the tower comes on and says, United 93, you are cleared for any runway? And the pilot comes back and says, you want it on a runway?
That is the incident. They brought the aircraft down. It did cartwheel. but they did get it down, and they did have survivors. And although it's a tragic crash, it's an example of a successful CRM where the pilot created an environment in there where they were able to do basically what was considered impossible to bring that plane home.
Roger, sir. Yeah, that's a closed runway. That'll work, sir. We're getting the equipment off the runway, and they'll line up for that one. How long is it? 6,600 feet, 6,600, and the equipment's coming off. Isolate this.
So that was really the defining moment of CRM. So again, we look back and we say it was a tragic accident, but in aviation they look back and said it was a huge success for CRM to save at least, I think, 60% of the passengers survived that incident. And a lot of changes came out of that. If you look at, what happened to the engine, why did the disc explode? Well, it exploded because there was an inclusion in the metal. Again, they went to triple melt after that on that metal.
Wow.
They had better inspection procedures. They separated hydraulic systems. The DC-10 never really recovered in respect to its
An somewhat intrinsic design flaw.
But that knowledge spread out through the industry, right? So all those things are incorporated into every aircraft we fly today.
John, I cannot thank you enough for first of all, let me thank you for a career that's obviously been dedicated to making our world a whole lot better and safer, and allowing us to proceed to sunlit upland fields. Thank you you brought that culture, I think, everywhere you've been. I was delighted to meet you and see how much you saw the world in terms of systems and keeping us all safe. And for those of you out there who are watching the wonderful world of The Doctor Is In, stay safe, be healthy, and tune in again. Thank you.